Good afternoon, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, our topic of discussion is point estimation. Let us look into the details with the help of slides. So, in the statistical inference or inferential statistics, which you have come across in your second semester, that is probability and statistics, the process of drawing conclusions about populations from samples and that are subject to the random variation. That means in inferential statistics, we will study about a population basing on the sample, that is subpart of the population, and we'll try to judge the parameters of the population by using the sample data. So these are subject to random variation due to the sampling conducted in random process. There may be little variations whenever you pick up a new sample. We will learn three basic statistical inference techniques in the rest of the course, that is estimation, hypothesis testing, and lead. So in this topic, we are going to concentrate on estimation, especially on point estimation. So estimation theory is a branch of statistics that deals with estimating the values of parameters based on empirical data that has a random component. That, as I told you a few minutes ago, as in the estimation theory, they'll try to estimate a population parameter by using the sample, a subpart of the population, and we'll use the sample statistic, that is formula, mathematical formula, which will gives you the correct results over the population parameter, and we'll try to predict or estimate the value of mu basing on the sample statistic. And this process of estimating the population parameter using the sample statistic is called estimation. And what do you mean by estimate? Now let us look into the definition of an estimate. Estimate is a single value that is calculated based on samples. That means whatever the value we have calculated by using random sampling and the sample statistics, the value is called estimate. So estimate is nothing but the value of the parameter obtained by using the sample statistical calculations. And estimator. Now let us look into the definition of estimator. Let us try to understand this concept with the help of an example. Suppose if I'd like to calculate the average height of students of IARE college. Okay, that means my subject of interest is to calculate the average height of IARE college students. So my population is the IARE college students and their heights. Actually, the heights of IARE college students. So I'll pick up 10 students from each branch, like 10 students from CSE, 10 students from EC, and 10 students from Aeronautical. Like that, I'll pick up 10 students and I'll form a sample. I'll form a sample because there will be several few thousands of IARE students, and it is not possible to measure the heights for all students. I go for sampling. I'll collect a sample which comprises of 10 students from each specialization, and I'll measure the heights of that sample, and I'll calculate the average, that is called X bar. Now, with the help of X bar, I'll try to predict the average height of the whole college IARE, that is represented by mu. So what here I'm trying to do here, I'm trying to estimate the average height of the whole college by using the average height of the sample. So this is called estimation, and the value I have obtained basing on the sample is called estimate, and the formula which I am using on the sample to estimate the population parameter is called estimator. So what is the difference between estimate and estimator? Estimate is nothing but the value we have calculated by using the sample data, and estimator is the formula which we are applying on the sample to estimate the population parameter. And the entire purpose of estimation theory is to arrive at an estimator which takes the sample as input and produces an estimate of the parameters with their corresponding accuracy. So in the main objective of estimation theory is to arrive at an estimator which will predict the value of the population parameter correctly. Okay, so this is the main objective of the estimation theory. Now, let us look into the concept of parameter. What is a parameter basically? A parameter is a statistical constant that describes a feature or phenomena about the population. That means when we try to describe the population, we'll use some statistical concepts like mean. That means mean is nothing but accumulation point, you can say, or gravitational point, or the point around which the data points are being circulated. Okay, and median, like mode, variance. So there are several statistical constants. You know what do you mean by mean, and what is the role of median, what is the role of mode and variance, standard deviation, etc. All these are called parameters because they will describe something about the population. Okay, so examples of parameters you can see in the binomial distribution, the population proportion of success, that is P, the success proportion of the population is a parameter, and we will try to estimate the value of the proportion of success for the population by using the sample proportion rate of success. Okay, and the mean mu is also a parameter, and standard deviation sigma is also a parameter. So there are several parameters which will describe the population. Okay, so now what are the different types of estimates? Okay, or different methods of estimation. So basically we have divided the methods of estimation in statistics into two types, namely point estimation and interval estimation. Now, what is the basic difference between point estimation and interval estimation? In the point estimation, we'll try to find the value of mu with the help of the sample mean x bar, and we'll express the value of mu as a single number like 50. If we are trying to measure the height, we'll try to express it as a single number as 5.6 inches on an average. That is, the height of IARE students on an average is 5.6 inches. Okay, here we are trying to express the estimated value of population mean as a single number. This is called point estimation. Instead of that, if we express that mu will vary between 5 to 6 inches. Okay, that means we are predicting that the average height of students in IARE college will vary from 5 to 6 inches. That means we are trying to estimate mu in terms of interval. This is called interval estimation. So in the point estimation, we'll try to predict the value as a single number, but in interval estimation, we'll try to predict the value as an interval. Now, our major concentration in today's discussion is point estimation. So let us confine to the point estimation. So let us take some examples, basic examples, which will describe the point estimation. That is, the sample proportion will be a point estimate of population proportion of success. Similarly, sample mean will be an estimate, a point estimator of population mean. Similarly, the sample variance will be a point estimator of population variance. So these are the basic examples of point estimates. Okay, and the value we have obtained for this population parameters by using the sample are called point estimators. Okay, and so we have different symbols, like for mean we will use x bar, and for variance we use s square. For the population proportion or sample proportion we use p. So various symbols and acronyms are there to represent the parameters as well as the sample statistics. Now let us recall the formula of sample mean. That is, in your 10th class statistical things, you can recollect that what is sample mean or what is the mean of a data. So now our interest is in this example, let x1, x2, so on xn be a random sample from any observation cap f suffix theta for which the mean exists and is equal to theta. We may want to estimate the mean of theta of distribution. For this purpose, we may compute the mean of distributions x1, small x1, small x2, small x1, and x bar can be taken as point estimate of theta. That means when we want to calculate the mean of a population, we'll take a sample that is x1, x2, x3, so on, xn, and we'll calculate x bar. Okay, which is nothing but sum of this formula, sum of all observations divided by number of observations. So here this x bar, which could be summarized as summation xi, I runs from 1 to n over n, is called the point estimate of the population. So in this way, we can understand the sample mean as a point estimate of population. Okay, and here we can also see that in a sample collected from Poisson, the population which is following Poisson distribution. Let us recollect what is Poisson distribution and what is binomial distribution. When uh, we have when we the distribution is said to follow Poisson distribution if the probability mass function of the population is defined as e power minus lambda power x by x factorial, where x runs from 0, 1, 2, so on infinity. And we will call the distribution will follow binomial distribution if its probability mass function is given by ncx small p power x small q power n minus x, and x will be a finite but discrete, that is 0, 1, 2, 3, so on. So this is the probability mass function of Poisson distribution. Now we have taken a sample from a population which is following Poisson distribution, and the Poisson mean is lambda. You have come across this fact in your probability and statistics curriculum that the mean of the Poisson distribution is lambda, and also the variance of the Poisson distribution is lambda. That is, both mean and variance are equal to lambda for the case of Poisson. Now, as usual, the sampling mean that is collected from the Poisson distributed population again is a point estimate of the population. That is what is described in this particular example. Now, what are the different qualities? That means if you want to say that a point estimator to be an efficient or a good predictor, of the population parameter, it should possess some qualities. Now I'm going to list out those qualities and I'm going to discuss those qualities one after the other. Okay, so the first quality that a point estimator to be known as the point estimator to be known as the best estimator of population parameter, it should possess the following qualities. First one, unbiasedness. Second one, efficiency. Third one, consistency. That means if an estimator possesses these qualities, like if the estimator is unbiased, if the estimator is efficient, if the estimator is consistent, then it will be called as the best estimator for the population parameter. Now, what do you mean by an unbiased estimator? What do you mean by an efficient estimator? And what do you mean by the consistent estimator? That we are going to see now. So, unbiasedness verify the fact whether the mean of the estimator, that is the sample mean, is close to the actual parameter, that is population mean. That means unbiasedness will clear your doubt whether your estimator, that is x bar, is very close to the population parameter, that is mu. And the efficiency will clear the doubt whether the standard deviation of the estimator is close to the actual parameter. That means if it is found that the estimator is unbiased, then you'll check its standard deviation, that is sample standard deviation, and we'll verify whether it is close to the population standard deviation sigma or not. If it is successful, that means x bar is close to mu, s is close to mu, then we'll check the consistency. The consistency will clear us that whether the probability distribution of the estimator becomes concentrated on the parameter as the sample size increases. That means if we go on increasing the sample, okay, is there is consistency sustained in the sample mean, that is x1 bar, x2 bar, x3 bar. Okay, are they converging towards mu or not? So see, the first one, unbiasedness, will verify whether x bar is close to mu or not, the parameter and the samples. And if efficiency will tell you whether standard deviation s is close to sigma or not, and consistency will verify whether as you go on increasing the sample size, whether the sample means sequence is going to converge towards the mu or not. So these three things will be clear from the concepts or the calculations of unbiasedness, efficiency, and consistency. Now let us look into the measurement of unbiasedness, measurement of efficiency, and measurement of consistency. Before that, I'd like to coin few important differences or possible discrepancies between sample statistics and the population parameter. Even though you take good sample or big sample, there might be some difference between your estimation and the original value. Definitely there will be some discrepancy. So in order to calculate the discrepancy, the level of or degree of discrepancy, we'll take the help of some calculations called sampling error or the bias or the mean squared error. Okay, let us look into those things in detail. In the sample error, the expectation of the statistic, okay, that means you are trying to calculate the expectation of x bar or the sample statistics, and you're trying to estimate theta. Okay, so the difference between your estimation and the original value, the marginal difference, is called the sampling error. That means whatever the difference between x bar and mu, of course you can apply more. It tells you what is the range of error that you have committed while selecting the sample. Okay, while collecting the sample, you have committed some error, like you have picked a small sized sample, or you may have picked wrong observations. Whatever the errors that you have committed while collecting the sample from the population, that is represented with this calculation, that is theta cap minus theta. And the expectation of theta cap x minus theta, that is expectation of theta cap x minus expectation of theta. Because theta is constant, it will be equal to expectation of theta cap x minus theta. This particular difference tells you whether the estimator is biased or not towards the population parameter. That is, theta cap is biased towards theta or not. Okay, that means if it is positive, you say that it is positively biased. If it is negative, you say that it is negatively biased. And if it is zero, you say that there is no bias between sample statistics and population parameter. Okay, So third calculation is mean squared error. That means the expectation of theta cap of x minus theta whole square is called mean square error, and of course it will be automatically equal to the mean square error will always be equal to variance of theta cap plus biasedness of theta cap whole square. Okay, so the relationship between the mean square error and the variance and the bias, okay, you can easily understand by expanding this a minus b whole square, and by calculating you will get this thing. Of course we'll prove it little while. So the mean square error will always be equal to the variance of theta cap and the bias of theta cap, the square of its bias. Okay, so this is the relationship. Now a point estimate of theta cap is called unbiased if the bias is zero. I told you if there is no bias, it's called unbiased. So unbiased estimator is nothing but if the bias is zero, that is expectation of theta cap x minus theta is zero. So whenever expectation of theta cap x minus theta is zero, we call it as unbiased estimate. Okay, and you can observe that expectation of x bar minus mu. Let us calculate this. Expectation of x bar minus expectation of mu. Expectation of x bar minus mu. What is expectation of x bar? Expectation of x bar, you know that it is nothing but mu. So mu minus mu, that is equal to 0. So expectation of the difference between the sample estimator and the population parameter is 0. That means we say that x bar is unbiased estimator of mu, unbiased estimator of population mean mu. Okay, in a similar way, the modified sample variance will be an unbiased estimator of the population variance because the expectation of s square minus sigma square is 0. Now what do you mean by efficient estimator? So in the let us first discuss the difference between unbiased estimator and biased estimator. I am going to draw two diagrams which will describe you about unbiased and biased estimator. Here, this is mu, which we are trying to predict. Okay, and this is, you can say, x bar. Okay, and what you are observing, you are observing that the line x bar it is symmetrical about the line x bar. That means it is equally spread on both sides. Okay, but now I am going to draw one more graph. This is x bar. So what you are observing here, the right side part is more wider than the left side part. That means more data has been falling on the right side than the left side, and hence this is biased. So what do you mean if the concentration of data towards both either side of x bar is equal? That is, if 50% of data lies to the left side of x bar and 50% of the data lies to the right side of x bar, then x bar is called unbiased estimator. But if 70% lies on the right side and only 30% lies on the left side, then it is called biased estimator. So that is the geometrical interpretation of unbiasedness. Now, what is efficient estimator? Okay, now let us verify. Let us try to understand the concept with the help of two graphs. Here we have a graph Okay, and here we have another curve. Okay, this represents x1 bar, that is one estimator of population parameter mu, and this represents x2 bar, which is another unbiased estimator of population. First, let us check whether x1 bar, x2 bar are unbiased or not. If you see on either side of x1, the data are equally spread. That is, on this side and this side, both sides of the center line, the data is equally spread, and hence the first curve, that is this curve, is unbiased estimator of mu. Similarly, for x2 bar also, on either side of the center line, the data is equally spread. So both are equally concentrating on mu. So we can say that both are unbiased. Now we want to find which is better estimator when compared with the other. That is, whether x1 bar is better than x2 bar or x2 bar better than x1 bar. For that we will consider the dispersion from the center. That means the data here are spreading within this range. Okay, within this range. But here the data has been spreading with this range. Okay, now which spread is higher, whether sigma 2, that means sigma 2 is occupying more space and sigma 1 is occupying less space. So this tells that sigma 1 is efficient than sigma 2, because sigma 2 is taking large storage to collect the data. That is, spread is more longer from the center. This data has been spread to the longer distances around the center. But in case of sigma 1, that is second curve, the data has been very nearer around the center with the distance of sigma 1. So this, because the radius is sigma 1 and radius sigma 2, sigma 1 is less than sigma 2. We call that x1 bar is the x2 bar is the more efficient estimator than the first estimator, that is x1 bar. So when we have more than one unbiased estimators, we'll try to judge the betterness of the estimators by using the efficiency, that is the variance. If variance of theta 1 cap is less than variance of theta 2 cap, then we call the first estimator x1 bar is more efficient than the second estimator x2 bar. Okay, so now what is most efficient or minimum variance unbiased estimator or most efficient estimator? Suppose we have several estimates like theta 1, theta 2, so on, theta n of the population parameter theta, and all these are unbiased estimators. Let us suppose that all these are unbiased estimators of population parameter theta. Then and suppose variance of theta 1 is lesser than variance of theta 2 and variance of theta 3, so on, variance of theta n. That means theta 1 has less spread when compared to the remaining parameters. Okay, and hence theta 1 is called most efficient estimator than other parameters. That means theta 1 is the most efficient estimator, even though all are unbiased. Because variance of theta 1 is lesser than the variance of other parameters, we call theta 1 as most efficient estimator. Okay, so efficiency will be determined with the help of variance or the spread. Okay, and minimum variance unbiased estimator or most efficient estimator, both are same, nothing but the unbiased estimator with least variance is called minimum variance unbiased estimator. Now let us take an example to understand this concept with more in a better way. Where, the shape of a normal curve is reverse bell shape. You know this. Okay. Now for the normal population mean mu, normal distribution means it will have two parameters, mean and variance. We have two unbiased estimators, that is expectation of sample mean is equal to mu, as well as expectation of sample median is equals to mu. But when you take the variances of mean and median in terms of normal distribution. There is the variances of sampling distribution of mean and variance of sampling distribution of median. You consider both of them, that is sigma x bar and sigma median. Okay, you will observe that sigma x bar, okay, is sigma, and sigma median, uh, sigma x bar will be sigma by root n, and sigma median will be pi sigma by root n. So you'll observe that sigma by root n is lesser than pi sigma by root n. And hence you declare that the sample mean is more efficient estimator to the population mean than the sample median in the case of normal distribution, because the sample mean has this standard deviation, the sample median has this standard deviation, and this is lesser than this. That means sample mean is more efficient estimator than the sample median in the case of normal distribution. Now, let us take an analogy. An analogy considers shooting with a rifle having telescopic sight. You know, a rifle with a telescopic sight, that means you can fix targets at a longer distance and you can easily reach them. A given target can be missed for two reasons. Even though you are trying to shoot it through your rifle, which has telescopic sight, there are two reasons or two constraints which will prevent you from shooting your target successfully. First one is the marksman may be unskilled and shoot all over the place. That means if your target is this and you're trying to shoot it from here, okay, this place, the marksman means the shooter, and you may miss the target due to your unskilledness, and you may shoot in the surroundings, not at the exact target due to unskilledness. Okay, sometimes a meter to the right and sometimes a meter to the left. That means you may miss the target with a less distance, sometimes 1 inch right or 1 inch left with a less distance. Okay, in this case, the shots have larger variance. Another person may consistently hit a point 20 centimeters to the right of the target. The telescope sight is not set right, and this is called systematic. But when you didn't set the telescope angle correctly, okay, while shooting the target, it may continuously, even though you are shooting correctly, it will continuously hit the targets 20 inches away, because you didn't set the angle. That means there are two kinds of mistakes being committed. One is due to your lack of concentration, and second is due to the error in the machinery. That is, one is human error, second is machine error. So the second kind of error is called bias. The first error is called variance. So I'm going to describe the difference between bias and variance. So if you are not able to shoot the exact target due to your lack of concentration, that is called variance. But if you are not able to shoot the target due to wrong fixing of machine, that is called bias. Okay, so that is the difference between variance and bias. Now, here we are going to see that the sample variance is not at all an unbiased estimator of population variance. That means we are going to prove that the sample variance is not equals to the expectation of sample variance is not equal to population. So how to overcome this? That we will see. First, we'll prove this fact. For that, we are considering this one. Okay, we are considering this one, that is 1 by n summation k is equal to 1 to n xk, the points, minus x n bar, okay, whole square. And we apply expectation on both sides. We apply expectation on both sides, and hence we'll get this term. Now, 1 by n expectation of summation xk, k is equal to 1 to n, plus xn square, summation xn square, k is equal to 1 to n, xn bar square, minus xn bar into summation xk, k is equal to 1 to n. By using a minus b whole square, we'll arrive at this step. Okay. Now, summation xk, k is equal to 1 means sum of observations, and hence we'll have 1 by n, 1 by n, and this is nothing but n, n mu, we can say, or oh, okay, x square, xk square it is. So, it is nothing but mu square plus sigma square. Okay, summation x square always will be equal to mu square plus sigma square from the definition of variance. And summation xn bar square is nothing but sigma square by n. Sigma square by n, because xn square will comes out and it becomes sigma square by n. And this becomes minus 2 and this becomes the first one becomes mu square plus sigma square by n, and the second one becomes mu square plus sigma square by n. And once you release the brackets, mu square will be cancelled, and you will get this is sigma square minus sigma square by n, that is n sigma square minus sigma square by n, that is n minus 1 sigma square by n. That means you have proved that expectation of sample variance is equal to n minus 1 by n sigma square, which is not equal to sigma square, and hence the sample variance is not at all an unbiased estimator of population variance. So, how to overcome this? So, to overcome this failure, we'll introduce the modified sample variance. That is, when we replace the sample variance, that is summation xi minus mu whole square by n with the help of the modified variance s bar square, that is summation xi minus mu whole square by n minus 1. And we observe that expectation of s bar square can be written as expectation of 1 by n minus 1, you can write it out, expectation of summation xi minus mu whole square. Okay, and you can write n by n minus 1 expectation of summation xi minus mu whole square by n. And just now we have proven that this is equal to n minus 1 by n into sigma square. N minus 1 cancels, n cancels, answer will be sigma square. That means we have proved that the modified sample variance expectation is equal to the population variance, and hence s bar square is an unbiased estimator of sigma square, but s square is not an unbiased estimator of the population variance. Okay, now with this we have looked into an example where a biased estimator, that is s square, and an unbiased estimator, that is s bar square, to the same population parameter, both are trying to estimate sigma square, but this is failing in that because expectation of s square is not equal to sigma square. This is successful because expectation of s bar square is equal to sigma square. Okay, so this is unbiased estimator and this is biased estimator. Now, so that is what summarized here. So the unbiased estimator of the population variance is given by s bar square, that is equal to n minus 1 by n s square. Okay, because as we have seen that expectation of s bar square is equal to n minus 1 by n into expectation of s square, that is equal to n minus 1 by n into n by n minus 1 sigma square, and hence sigma square. Okay, now So we have observed that x bar is an unbiased estimator of mu, and s square is not an unbiased estimator of mu, but s bar square is an unbiased S square is not an unbiased estimator of population variance, but S bar square is an unbiased estimator of population variance. Now, when it comes to the population proportion success, that is small p bar, it will be an unbiased estimator of population success proportion capital P when you take the case of binomial distribution. Now, finally, I'd like to conclude this lecture with a small example on the point distribution. A puzzle, we can call it as a puzzle or an understanding over point distribution. A coin C1 has the probability P of turning up head, and a coin C2 has the probability of 2P of turning up head. That means we are tossing two coins. This coin turning to head, the probability is P. This coin turning to the head is, this is C1, this is C2, is 2P. Okay. And we know that P ranges between 0 and half. He has given that the rate of success of that coin, okay, is always ranges between 0 to 50%. That means it is less than 50%. Okay, and that means Q will also ranges from 50 to 100%. Okay, that means it will range from 1 by 2 to 1, because it compensates, because P plus Q is equal to 1, automatically we have this conclusion. Now you can choose all tosses from C1 or all tosses from C2 or some tosses of each combination, total 20 tosses. If your object is to estimate capital P, what you do? What choice you will prefer? Whether you will consider all tosses from C1 or you will consider all tosses from C2, or you will combine the tosses from C1 and C2. What is your selection? Okay, if we choose to have all 20 tosses, only 20 tosses, maximum number of tosses is 20 tosses. Okay, and from C1 we get x1 so on xn. These are the n, that means 20 outcomes. Okay, and the mean square error of this small sample proportion P for this sample we can calculate the sample proportion P, okay, and its mean square error, which will be P into Q by N, that is P into Q by N. This is the mean square error. Okay, and for the sample for 20 tosses, that is y1, y2, yn, okay, for the Bernoulli trials with 2p, parameter 2p, okay, the estimate, the mean square error will be like p into 1 minus 2p by 2. So for the first one, p into 1 minus p by 2. For the second one, p into 1 minus p by 2. As p ranges between 0 to half, okay, and 1 minus p ranges between half to 1, 1 minus p ranges between half to 1, we have 0 less than p into 1 minus p is less than 1 by 2, and p into 1 minus p by 2 will be less than 1 by 4. But whereas when you consider p into 1 minus p plus p or minus p by 2, okay, that means p into 1 minus p by 2 minus p square by 2. That means 1 by 4 minus some quantity. That means what you are observing that the mean square error, that is p into 1 minus p by 2 and p into 1 minus 2p by 2. The mean square error of this is lesser than the mean square error of this. That is why we consider that it would be better choice if we continue go on tossing 20 times the second coin rather than the first coin. So, because that means here mean square error plays a vital role. Mean square error for which estimator the mean square error is less, we prefer that estimator and we consider that estimator as efficient than the other. Here we have two estimators, that is P and 2P, for 2 coins C1 and C2. But here for this estimator we have less mean square error, but for this estimator we are having higher mean square error, and hence we consider tossing C2 will be wiser choice than tossing C. In this way, we could understand how important role the bias and the mean square error and the variance will play in judging an estimator as efficient when we have a set of unbiased estimators for the population perimeter. With this, I'd like to conclude this lecture on point estimation. In the next lecture, we'll meet with an interesting topic called interval estimation. Okay, thanks for your patience listening. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.